Hey guys, welcome back for another week. We actually only have the 3 weeks left of school. Make sure that you're taking a look at the calendar and that syllabus that I put out so you know what we have coming up here. What we're going to be talking about all this week is this topic called stoichiometry. And we've actually talked a little bit about stoichiometry before in class. It's something that I said the father of modern chemistry, Antoine Lavoisier, is greatly responsible for setting into motion. When I talk about stoichiometry, you might also hear me shorten it down to stoic. Stoichiometry, same thing when I say it here. So let's go ahead and we'll get started on some of these PowerPoint slides, and then we can go inside and use that whiteboard wall a little bit. Okay, so to start off our lecture on stoichiometry, I want to introduce this topic called the mole bridge. Hopefully we're getting comfortable with this idea of the mole. The mole is a counting tool. It's a number. Just like a dozen means 12, a mole means Avogadro's number, 6.022 times 10 to the 23rd. So when we talk about the mole bridge is it's like a ratio. It's a bridge. It's a connection between our reactants and our products. The mole bridge is a set ratio between the coefficients of the reactants and the products. I'm going to end up saying that a few more times. If we look at this reaction specifically here, this is a reaction that we've done before. It's the combustion of isopropyl alcohol. It's what happens when you catch rubbing alcohol on fire. We did this in the whoosh bottle. This is a balanced reaction. It follows the law of conservation of mass. I've got 6 carbons on one side, 6 carbons on the other side, 16 hydrogens on one side, 16 hydrogens on the other side. The oxygens are equal to. It's balanced. What I'm telling you, the mole bridge is the ratio of these balanced coefficients. So in other words, for every 2 molecules of isopropyl alcohol that get burnt up, I'm going to need to use 9 molecules of oxygen gas. I'll produce 6 molecules of carbon dioxide and 8 molecules of water. That's what these coefficient means. That's how this reaction is going to balance. I'm telling you that ratio is always going to be the same. Even if the numbers themselves change, the ratio between them will stay the same. So maybe I had twice as much. If I had 4 molecules of isopropyl alcohol, I would need 18 molecules of oxygen gas. I'd make 12 of carbon dioxide and 16 of water. I just doubled everything. I could multiply it all by 12. 2 dozen molecules of isopropyl alcohol will need 9 dozen molecules of oxygen, 6 dozen carbon dioxide, 8 dozen of water. But a dozen is just a counter, just like a mole is just a counter. So if we read this top part here, we can think about the coefficients in 2 ways. We can imagine a really small number of molecules that are reacting, like just 2 molecules of isopropyl alcohol. Or we can imagine entire moles of the substance reacting together. 2 moles of isopropyl alcohol, 9 moles, 6 moles, and 8 moles. It's no different than saying 2 dozen, 9 dozen, 6 dozen, 8 dozen. It's just a bigger number. A mole is a bigger number than a dozen. So this lets us go from a very small microscopic scale to a big macroscopic scale. The mole bridge. This is the last time I'm going to say it on this slide. The mole bridge is a ratio of the coefficients between the reactants and products. So let's see what one of these looks like in action here. I know it's dimensional analysis that we're looking at here. This is what we're going to need to be able to do. This is why we've been practicing those dimensional analysis skills. Let's take this slide just a little bit at a time. Putting it all together. This is why we need stoichiometry. We're combining all these ideas that we've already talked about. So let's figure out if we had 10 grams of rubbing alcohol, isopropyl alcohol. If I had 10 grams of rubbing alcohol and I caught it on fire, how many grams of water would I make? I'm using this same reaction as my reference. I'm burning up rubbing alcohol. I'm burning isopropyl alcohol. For every 2 moles, I'm going to make 8 moles of water. That's my mole bridge, 2 to 8. 2 moles isopropyl alcohol, 8 moles water. 2 to 8. Remember that ratio, that mole bridge. So putting it all together. When we do this dimensional analysis, when we do this stoichiometry, we need our units to cancel out. So if I'm starting with 10 grams of isopropyl alcohol, I'd better have grams in the denominator of my next fraction. This next fraction that we're looking at here is the molar mass of this alcohol. We've done molar masses before. You might need to recheck your notes. But the way that I'm getting this number, this 60 gram number, it's from all the atomic masses from the periodic table. I've got 3 carbons, so I said 3 times the atomic mass of carbon, 8 times the atomic mass of hydrogen, and then 1 times oxygen. That adds up to that 60 grams here, 60 grams in 1 mole. So I took my 10 grams of alcohol that I'm trying to catch on fire, and I converted it into moles. I did that using the molar mass. You could have done this step algebraically too, using the algebra formula. Now I'm working with moles of isopropyl alcohol. My next step is going to be the mole bridge. This is that ratio that I was talking about. For every 2 moles of isopropyl alcohol, I'm going to end up making 8 moles of water. It's the same as on this slide. 2 moles, 8 moles over here. It's that same ratio. 2 moles of isopropyl alcohol, 8 moles of water. And then my last step is to turn these moles of water into grams of water. I'm going to do another molar mass. I'm getting these numbers from the periodic table. 2 times the atomic mass of hydrogen. 1 times the atomic mass of oxygen. It adds up to about 18. So 1 mole of water is about 18 grams of water. If all of my units cancel out, the only thing I have left is grams of water. So I started with a pre-measured amount of alcohol. I knew I had 10 grams. If I burn it all, if I do this reaction, this combustion reaction, the predicted mass of water that I'm going to make is 12 grams of water. It seems like I'm adding mass. I started with 10 grams and I ended with 12 grams. Well, that's just because the mass is moving around. Some of it started in the air as that oxygen gas. And then it just kind of got transformed into something new. That mass of water just happened to be bigger than what we started with. This is still obeying the law of conservation of mass. I made sure of that when I balanced this reaction. Then I'm just doing conversions to change grams of one chemical into grams of another chemical. I still have to obey that ratio, that mole bridge. But then if you look, the first two and the last two here are really just molar mass equations. They're algebra equations that I've put into a dimensional analysis context. This might be a little bit easier to see when I work it out on the whiteboard in a second here. I think I'm going to go for 3 different examples today, just because this is one of the harder things that I'm going to go ahead and say this is the hardest thing that we're going to learn this year. And I think that we are going to need at least 3 examples on top of this one for it to start to make sense. So we're going to switch it over to the whiteboard inside now. Let's see if we can't do a few more of these stoichiometry problems, these stoic problems. Alright, so let's take a look at what one of these Stoic problems would actually look like. When you're given a stoichiometry problem, it's going to have two parts to it. It'll have a story problem part to it, and then it should give you a balanced reaction too. So my story problem part, if we take a look here, it says, if 50.0 grams of magnesium react with excess nitrogen gas, then how many grams of magnesium nitride will be produced? So I know that I started with 50 grams of one thing. I want to know how many of the other thing I'm going to end up producing, that I'll end up making. And then it gives me a reaction here. This is the same reaction that's being described in the story problem. Your first thing that you're going to want to do, number one, make sure that it's a balanced reaction. If I'm nice, I'm going to be giving you all balanced reactions to save you time. But it could be the case where you end up with an unbalanced reaction, and you've got to balance it, add in those coefficients before you can even start. If I gave you a reaction like this, the mole bridge that we're going to go with, the ratio, is 3 to 1 to 1. This is going to obey the law of conservation of mass, and now this is a balanced reaction. So there's my first step out of the way. I'm working with a balanced reaction. Now we're going to actually need to do this stoichiometry. This is the math that's basically dimensional analysis. It's set up that way. It's dimensional analysis that's been applied to a chemical reaction. There are actually two ways that I could do this stoichiometry. I'm going to show you both ways for this first example, and then I'll let you pick which one you prefer, and I'll just be showing one example for the rest of the problems that we'll do. So, the two ways that I could choose, my two options here. I could follow the question word, like I've been teaching you with these other dimensional analysis problems. I look for my question word, who, what, where, when, how, and I follow it until I know what it is I'm looking for. How many grams of magnesium nitride? So I can boil this question down to just a few words. How many grams of magnesium nitride? That's what I'm trying to figure out. And that could be my starting point. The other potential starting point is the given information. What information did the problem give me to start off with? I know that I'm starting with 50 grams of magnesium. So I could use that as my starting point too. I'm going to show both ways really quickly here. Let's start by using our starting point, our given information. I know that I'm given 50 grams of magnesium. That's what the problem tells me, so I can start there. 50 grams of magnesium. And I'm going to put that in the numerator. I'm going to set it up so that it looks like a fraction. Remember, that's how I like to do my dimensional analysis. Now, I know that this unit is going to end up getting canceled out. So what I like to do is take that unit, already go ahead and carry it down to the denominator. Grams of magnesium. I know that'll get canceled out. Eventually, I need to go over the mole bridge. I need to make the connection from reactants to products. And the only way to do that is to go over the bridge, the mole bridge. But I'm not in moles yet. I'm still working with grams. There's no such thing as a gram bridge. You can't go directly from grams of reactant to grams of product. You need to go through the middle, through the moles first. So I'm going to change this into moles of magnesium. Grams to moles. The way that I'll do that is with the molar mass. We've been doing problems like this, remember? The molar mass of magnesium is about 24.3 grams per mole. So 1 mole of magnesium has a mass of 24.3 grams, approximately. I found that on the periodic table. Remember how we look up those molar masses. So now I'm into moles. Now that I'm working with moles, I'm ready to go over the bridge. I can do the mole bridge now. And remember, we worked out that mole bridge earlier. It's 3 to 1. For every 3 moles of magnesium, I'll produce 1 mole of magnesium nitride. 3 to 1, 3 to 1. Now I'm over here in my product side. I started with something from the reactant. I went over the mole bridge. Now I'm dealing with the product. I'll carry this unit down, moles of magnesium nitride. It's going to be really useful to write out the entire unit. I know it's a pain, but it'll help you keep track of everything. And I want to convert these into grams of magnesium nitride. The problem asks me how many grams of magnesium nitride. So I made it to my ending unit. This is another molar mass problem. I need to know how many grams are in 1 mole of magnesium nitride. And I'm going to use my periodic table again for this. Atomic mass of magnesium, multiply it by 3, the subscript. Atomic mass of nitrogen, multiply it by 2, and then add those together. It's going to be about 100.9 grams of magnesium nitride. At this point, I'm ready to solve. All my units cancel out. Moles of magnesium, moles of magnesium, moles of magnesium nitride, moles of magnesium nitride. The only unit that I have left is grams of magnesium nitride. And that's what the problem is asking me for. So I could go ahead and put this into my calculator from here. It's about 69.2 grams of magnesium nitride. That's the way that I prefer working from what I'm given. But you can do this in reverse too. Let me show you that. It's going to be very similar. What if instead I followed the question word? The question word says, how many grams of magnesium nitride? So what if I started there? Starting with grams of magnesium nitride. I know that I need to go over the mole bridge, so let's convert these to moles. It's the same number that I already worked out. I already know the molar mass of magnesium nitride. It's 100.9. So now I've taken my grams, I've changed them into moles. Now we can go over the mole bridge. And remember that we said 1 mole of magnesium nitride will be produced for every 3 moles of magnesium. These are moles here, I forgot my unit there. Now I'm into moles of magnesium. I'm on the other side of the bridge. I want to use these moles to convert into grams of magnesium. So I'm going from moles of magnesium to grams of magnesium. I've done this art problem already too. It's about 24.3. And then finally, I'm going to use what the problem gave me, those 50 grams of magnesium. You can see that all my units still cancel out. Grams of magnesium, grams. Moles of magnesium, moles. Moles of magnesium nitride, moles. The only unit that I have left is grams of magnesium nitride. You can actually see that these 2 different approaches to the problem are basically just reverses of each other. I did all the same work. This one's still in the numerator. This is still in the numerator. Numerator, numerator, denominator, denominator. It turns out I'm doing the same exact work. I can just approach it from the start and go that way, or from the end and go the other way. It's just if I'm going from the product side as my starting point or the reactant side. as my starting point. Either way, I'm going to get the same answer. It is a lot of work to do these stoichiometry problems. This is not something that's going to be fast for you, but it is a really, really important skill for us to have. We're going to do 2 more examples. I'll pick up the pace just a little bit, but I still want to show all my work so that if people are copying this work into their notes, that they'll have time to get it all down. 2 more, here we go. Going for example number 2 here. So, let's take a look at our story problem first, and then we'll take a look at our reaction, then we'll get started. If 4.0 moles of hydrogen gas react with excess chlorine gas, how many grams, this is hydrochloric acid, how many grams of hydrochloric acid will be produced? So the reaction that we're looking at here, this is a reaction that lets us make hydrochloric acid. You can combine hydrogen gas and chlorine gas to do this. Now, the reaction that I gave you this time is already balanced. It obeys the law of conservation of mass. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. I don't need to do anything special here. My reaction is already balanced. My mole bridge is 1 to 2. For every 1 mole of hydrogen gas, I will produce 2 moles of hydrochloric acid. I could start it either way, remember? This time I'm going to show it the way that I prefer, again, starting from what I'm given. I'm given that I have 4 moles of hydrogen gas. So I'm going to start with that piece of information. 4 moles of hydrogen gas. That'll be my nice starting point here. I can go ahead and carry that unit down already. I know that this unit is going to end up getting canceled out. I like to go ahead and already carry it down. Now, this problem is slightly different from the last one that I showed you. Instead of starting from grams, we're starting from moles. That actually makes the problem easier for us. If we're already starting in moles, then we can immediately go over the mole bridge. The mole bridge, remember, is the ratio of those balanced coefficients. And remember, I said that ratio. It's 1 to 2. For every 1 mole of hydrogen gas, I will produce 2 moles of HCl, hydrochloric acid. I can carry that unit down. And then I'm almost at the end here. The question asks me how many grams of hydrochloric acid will be produced. I've made it all the way to moles of hydrochloric acid. Now I just need to convert those into grams. This is another molar mass problem. I'll use my periodic table to come up with these numbers. It turns out that this molar mass is just about 36.5 grams per mole. I'm double checking myself here. Yeah, that's right. So 36.5 grams per mole. All of my units cancel out. The only thing I have left is grams of hydrochloric acid. But that's good. That's what the problem is asking me for. I would do my math here. 4 times 2 times 36.5. And I'm going to end up with about 292 grams of hydrochloric acid. So, I made sure that my reaction was balanced. It was already balanced. I started with what I was given. That's this first fraction here. 4 moles of hydrogen gas. Because I started with moles, I went over the mole bridge. 1 to 2, 1 to 2. And then my last fraction, this one here, this is a molar mass, the molar mass. I looked up the atomic mass of hydrogen and the atomic mass of chlorine, and I added those together to come up with this 36.5 number. So there's our second example down. Now let's do one more, and then hopefully you'll be able to do the homework at that point. If you're not though, remember, email me, ask people in the chemistry chat room, come to office hours. We can make sure that you get those answers. But for now, let's do one more example on the wall here. So one more example for today. This reaction, let's go ahead and read it first. If 10 grams of copper react with excess silver nitrate, then how many grams of silver will be produced? This is actually a pretty cool reaction because it produces solid silver. This is a way to actually chemically make pure silver. Pretty cool reaction. I had the pleasure of doing this one once. So, it is already balanced for me. I've got my coefficients here, 1, 2, 1, 2, and that's balancing everything out. So I don't have to do that step. I'm already working with a balanced reaction. This time I'm going to show it the other method. What if I follow the question word? My question word is how. How many grams of silver? So I'm starting with grams of silver. The problem asks me how many grams of silver, so I'm going to start with grams of silver. Now, I actually don't know how many grams of silver I'm going to end up with. That's the whole thing. That's what the problem is trying to get me to find out. So instead of just putting this over 1, like I've been doing in some of them, I'm going to put this over 1 mole. How many grams of silver are in 1 mole of silver? This is the molar mass of silver. I'll look it up on the periodic table, and it's just about 107.9 grams of silver. So great. I started with grams of silver, and I changed it into moles of silver. For my next fraction, now that I'm into moles of silver, I can do the mole bridge and make my way back to copper. The ratio here, 2 moles of silver, 1 mole of copper. 2 moles of silver, 1 mole of copper. My units are still canceling out. So far this is all good. I can carry this unit over because I know it's going to cancel out. Moles of copper. What I'm looking for in this third fraction here is another molar mass. I've got these moles of copper. Let's change them into grams of copper. And again, this is a molar mass. I'm going to find it from the periodic table. The molar mass of copper is about 63.5 grams per mole. But I don't have 63.5 grams. I only have 10 grams of copper. 10 grams of copper up there. That's my last fraction over here. I know that I need to cancel out these grams of copper. Where am I going to find those grams of copper? It's the 10 grams that I started with. All my units cancel out. Grams of copper, moles of silver. The only unit that I have left is grams of silver. And that's good, because that's what the problem asked for. How many grams of silver? I would multiply and divide, and my final answer here is going to be about 34.0 grams of silver. So I could really do this reaction in reality if I had 10 grams of copper and I submerged it in this silver nitrate solution, then I would end up making 34 grams of pure silver at the end of that reaction. Or at least theoretically, that's what I should get according to the math. Now, I don't prefer this way. I think I've said that before. I prefer starting with the information that I've given when I'm doing stoichiometry, but I want to show you that you can do it by following the question word. Since that's the strategy that I originally taught you, we can keep doing that. You can still follow that question word to start these problems. The most important part is just seeing that all of your units cancel out. It's a really easy way to double check yourself. If your units are not canceling out, you need to pause, take a breath, see what went wrong, because they should cancel out every time. You've got 3 stoichiometry problems for your homework tonight. If you're struggling with this type of stuff, definitely come to office hours or send me an email. Ask for help in the chemistry chat room. Use your resources here, guys. That's it for today. See you again tomorrow.